Welcome to the last class of the week. And we have a long weekend coming up. So we didn't end, but we had this picture last class period with the international date line here. And I figured a nice picture with the time zones would also be beneficial. So here's a picture that shows the time zones. It's the same prime meridian, but you see it shifted over, so you see, or the same time international date line. But you see the prime meridian is shifted over, and you can see the international date line is more complicated than was shown on the preceding slide. It doesn't show the funny excursion down there in the islands. You can see a lot more islands and understand, there's a lot of strangeness going on with the international date line. If you live in this region here, you're like, what in the world? How do I know what day it is? But more importantly, we have time zones. Why do we have, more importantly for this slide, why do we have time zones?
A good example is like how Chicago and St. Louis are on the same, I'm pretty sure, same time zone?
I think so.
I am?
Yeah.
Okay. But that way they weren't going both on local times, because like in Chicago it could be 12:59, but in St. Louis it could be 1:05.
Okay.
Back then. And that's why they consolidated it all into the time zone.
Okay, you used to have everybody just decide the time here is this. Now, it's been a really long time since people ran their times by the sun. If you were to run your time by the sun, there wouldn't be 24 hours in many days. Because if you go from noon to noon, the sun is going to, of course, be rising at different times. And noon would be when the sun is on your meridian. And so you can have, like he said, St. Louis and Chicago could be, 7, 10 minutes different from each other. And then when you say, let's have a meeting, let's meet at this time, you can have disagreements about, what time is that? So to make uniformity, we have time zones to try to make it more uniform. And so we have to agree on, how are we going to do those time zones? What does the military do for their time zones so that they'll all agree?
24.
They use a 24-hour clock. That's true, but that's actually not what they're doing regarding time zones. I think I mentioned this earlier first couple lectures. They use the time at the prime meridian. Doesn't matter where in the world you are, the time is the time at the prime meridian. They call it Zulu. You can also call it Universal Mean Time or Greenwich Mean Time. But they use...
Isn't it called GMT?
That would be Greenwich Mean Time. Yes.
So if for some reason they decided, hey, we're all going to do this at this time, some people would be like, technically, if you're not thinking prime meridian time, it'd be like 8 in the morning, and somewhere else it'll be like 9 p.m. or something like that. But to them, it's like one time.
Yes. So they just, you don't have to change your clock because no matter where you are, it's still going to be using the same clock. Mm-hmm. So that's one approach. And it actually seems like a really wise approach to me. The problem is we tend to get into routines like lunchtime is noon. And so if lunchtime is noon and you're on Greenwich Mean Time and you're here in Lincoln, Nebraska, noon Greenwich Mean Time is nowhere near where you would typically have your lunch. And so to make it so people feel more comfortable in the hours of the day, you go to work at 8, you come home at 5, doesn't matter what state you're in. That's why we have local time zones for the way that we do things. And of course, does everyone in the United States agree? No. We have, that Arizona holdout, they don't have daylight saving time yet. Why do we have daylight saving time?
Is it because the days have been way shorter or something?
Okay, the length of the day differs. Now, there's a lot of stories I have heard about why daylight saving time was approved. Some stories say that it was Ben Franklin's idea. Apparently, that's untrue. The general story that we understand to be true is that the point of daylight saving time is to try to save electricity, that it was a move that was made during wartime to try to save electricity. Because you have farmers get up with the light, go to bed with the light. And they figured if we could make things go like that for people who are working in factories, then it doesn't take as much electricity for them to be going about when the sun is not up. So the idea is you adjust the clock so everybody gets up essentially with the sun, and then they go through their day, and then in the evening they can come home and whatnot. So the idea is to have nobody in bed when the sun's up, if you can help it. Or to have nobody, more accurately, nobody up and walking when the sun's down if you can help it. A lot of people recently have disputed that that saves us any energy. And if it doesn't save us any energy, there's really not a lot of point in doing it. Everybody gets really happy when you get to sleep in an extra hour, but then everybody complains bitterly when you have to get up an hour early. There are some other ideas that have been proposed. The idea I like is convoluted as all get out. I'm like Tito Brahe here. I like the idea of us having two clocks. One is Greenwich Mean Time, and we'll use Greenwich Mean Time for scheduling our appointments. And one is the local clock. So if my local clock says noon, by golly, it's noon. And if I move somewhere, I could travel fast enough that I can make my clock go backward. That would be, no one would ever want that, right? But still, I think it'd be cool. Okay, so we have those time zones so people can all agree on a time. And you've got funny holdouts. I don't have to touch that. Back to tidal forces. We talked about the tides. I want to show you an animation for the tides. Now, I decided not to even try to do this on the tablet after this morning discovering that I wasn't going to be able to do my PowerPoint animation on the tablet. So I'm just changing over to the computer. And this is a simulator developed at University of Nebraska. They have a whole nice suite called Class Action for astronomy lessons. Kevin Lee has put all of this together. And so this here is something to help us understand better why we have high and low tides. So let's start by just letting this baby, let's look at it before we let it run. Notice that we have water bulging out on the side facing the moon. This is the moon here. And water bulging out on the side away from the moon. Why is the water bulging out on the side facing the moon as well as the side away from the moon? We talked about last class period, so it's a review question.
When the moon pulls away some of the water on the other side, it's also pulling the earth away from the water on the other side of the earth.
Okay? So what he said incorporated the key point. The key point is that the moon's pull is stronger on the side of the Earth that's closer to the moon, weaker on the side that's farther away. So we call that a tidal force when you have a gradient or a difference in the force depending on where you are. Is there a tidal force from the sun? You bet there is. But remember, the force of gravity is proportional to 1 over the separation squared. So for my example that I talked about before with me and Awan, so if I'm 1.5 meters and I go to 3 meters away, the force has been cut in half. If I go another 3 meters away, now it's only changed by a much smaller percentage because I went from from 3 meters, well, okay, 3 to 3, excuse me, would have cut in half again. If I went another 1.5, then it would not have gone down by another, factor of 2. It would have been smaller. And if I'm really far away from all I move away 1.5 meters, we're not going to notice the difference because it's too small of a variation compared to the total distance. So the sun being so far away, the tidal force, the difference in gravitational force from one side of the Earth to the other is pretty small from the sun. The moon being relatively close, it's a much bigger tidal force. So the moon is the primary cause of tides on Earth. Now, if I run this, we see as the moon goes around, we have the high tides following the moon. Of course, this isn't right. You can see I have 3 buttons and I only have 1 checked. So I'm going to, I wish this had a reset button. I'm going to wait for this to line up and then I'm going to turn it off. Okay, so, now I'm going to turn on the effect of the sun. Now the sun is going to be right in line with the moon here. So if the sun's right in line with the moon, what do you think the sun is going to do to the tides?
If it's in line with the moon?
Yeah.
Is it going to increase it?
It's going to increase it because the sun will be having tidal forces that are making high tides on the side closest and farthest from the sun, just like the moon. So there, see the tide got bigger. Now you see the phase of the moon. What's the phase of the moon here? When you look at the moon in this picture, how much of the moon you see is lit up? It's definitely more than half. You see the side of the moon that is facing the Earth. How much of that is lit up? How much of this is lit up? All of it.
Yeah.
So that's a full moon. So we're going to have this highest of high tides at a full moon. We call that a spring tide. So spring tide is your highest of high tides. Now let me run the animation. And we'll get over here and what's happening to the height of the high tides. Can you see a variation? What happened? It went down. Now, where is the high tide right now? Well, is the high tide here or here? It's not exactly even.
But it's still more towards the equator.
Well, the high tide is still facing the moon. But it's not nearly as big a difference between the side here and there. This is the lowest high tide we get, and we call the lowest high tide, that is the lowest difference between high tide and low tide. We call that a neap tide. What phase is the moon now? We're seeing the top now of the moon. How much is lit up now? Half. So at first quarter or third quarter, you have neap tides. So, if you're a surfer, which I assume we all are here in Nebraska, where, ocean is everything. When it's a quarter phase, first quarter or third quarter, you are not going to have the highest tidal surges. Now, does that mean you have the biggest waves? No. No, it doesn't. Because you're not surfing the high and low tide. But it does mean you're going to have a bigger variation, which I believe makes you more likely to have big waves. That is, the spring tides are more likely to have big waves than you are with the neap tides. But you're not surfing these tides, just to make sure it's really clear. Okay, let's keep this running. And we're going to come back around. What do you suppose is going to happen when it gets up here? Okay. we're back to the big high tide variation again. High tide here, low tide here, big difference. That's back to the spring tide conditions. And what phase is the moon now? It's a new moon. So you have the spring tides at new moon and full moon, the neap tides at first quarter and third quarter. But we're not done yet. You see there is a third option. Include the effects of the Earth's rotation. Remember me talking about the Earth's rotation on Wednesday? What's that going to do?
It's going to make the waves, the tides faster.
Okay, it's going to make the tides shift forward because of the Earth's spinning. So I'll turn it on. Now keep in mind, things are exaggerated here, but you can see the high tide shifts forward. So now if I run it, the high tide leads the moon. And that's how the Earth is pulling the moon along. It is very much like what happens when I swing this around in a circle. I'm actually moving my hand a little to pull it along, to keep it going. That's what the high tide is doing to the moon, to keep it going. Except for there's nothing slowing down the moon. Air is slowing down this body. No such thing out there for the moon. And so instead of just keeping it going, that pull is speeding it up. And as it speeds up, it gains more energy. As it gains more energy, it slowly moves away from the Earth. And so the moon is slowly moving away from us because of this tidal interactions.
So does the speed of the moon, like, revolving around the Earth, does it, like, varies around, like, a different time or so?
Okay, so there's two ways I can answer that. One is the long scale variation. As the moon is slowly moving away from us, the speed is also slowly dropping. That's one answer. So that's like in 100 years, the speed is going to be very minutely slower because it's farther away. The other answer is the moon, just like the Earth's orbit around the sun, the moon's orbit around the Earth is not a perfect circle. So yes, just like the Earth with the sun, when the moon is closer to the Earth, it's going to go faster. When it's farther from the Earth, it's going to go slower. Alrighty, back to the presentation. Talked about the tides enough here. We've already seen the picture of the Bay of Fundy. And we've talked about the neap tides and the spring tides. You understand the difference in those now. So let's talk about eclipses. Now, an eclipse, we all saw the eclipse last year, right? In fact, a couple slides I have, the best picture I took using this highly sophisticated instrument. I took a picture actually of what you could see through the telescope eyepiece that we had set up out there in the lawn using my camera. It's not very good. So we have some words I want you to see here. Umbra and penumbra. So if you look at the picture, we have the sun, and light from the sun is emanating in all directions, from all parts. So I have light from the sun going like this, and going like this, and going like this. Right? It's going in all those directions. Limiting cases are the only ones that are shown here, because otherwise your picture gets really busy. So there's going to be light going like this, right? And there's going to be light going like this. So the umbra is the region that is in full shadow. There is no light that can be in that umbra. So if you are in that umbra, it's complete shadow, no sunlight. If you exclude the fact that the earth causes some light to bend around it. So that's what the umbra is, full shadow. You see this place back here that says penumbra? You can see I had a lot of lines that went through the penumbra. Penumbra is the region next to the umbra. It's the region that's in partial shadow. And so penumbra is partial shadow, umbra is complete shadow. Usually when we talk about an eclipse, we want to talk about the umbra, the complete shadow. If you look at these pictures, if you're on Earth and you see this right here, yellow doesn't work as well on the white background. So if you see this right here, if you look at the sun, then that means you're in this region here where part of the sun is blocked, and that is a partial shadow situation. This picture here is what we call an annular eclipse. An annulus is a ring. And so you have a ring of sun around the moon. And I talked about this before. Now it should make a little more sense because the moon is sometimes closer and sometimes farther. When it's closer, the moon makes a bigger angle. When it's farther, it makes a smaller angle with our eye. So to get the annular eclipse, you need the moon to be a little farther than average and the sun to be a little closer than average. Or the earth a little closer to the sun if you want to be all frank and honest about what's moving. So the annular eclipse occurs when the moon is a little far and the sun is a little close. The full or total eclipse occurs when the moon is a little closer and the sun is a little farther than average. So that's the geometry that causes a solar eclipse. Or excuse me, yes, a solar eclipse. The moon passes between the earth and the sun. Now we're going to look at some different pictures. Here you can see sun, moon casts a shadow, and that shadow makes a little pinpoint on the earth. Like there's a picture. You can see where you're having an eclipse. The eclipse is, of course, reaching totality and something like that. Compared to the size of the earth, the region that has totality is very small. Okay, was everyone here for the eclipse last year? Okay. We were just barely inside the region of totality. If we would have gone to the far side of Lincoln, we would have seen a sliver of the sun the entire time. That's how close we were to not having a total eclipse. If we would have gone to Nebraska City, or actually Beatrice, however it's pronounced, if we traveled about 15 miles in the right direction, we would have had about a minute longer of totality because we would have been in the middle of it. Right? So it's not a very big region where you have totality because of the geometry that's making a small shadow on the earth. And so you can see if you're living out here, you're going to see, if you look through the eclipse glasses, you're going to see a partial eclipse. But it's going to be kind of a downer because it's not going to get that, didn't really get dark until just before the eclipse, right? We only had like 5 minutes or less and we could tell it's starting to get darker. So it's not nearly as exciting not being totality. So it's totally cool being here last year. I've been telling my students about it since about 2010. Finally happened. Now it's a letdown. I don't get to talk about it anymore. But where y'all going to be in 6 years? There will be another total eclipse. There are some towns that will be right in the center of both, which is awesome. Yeah.
Where would it be? Like,
I'm going to show you a map.
Okay.
Okay. Moving forward. Actually, I already talked about, I only put this slide in. I was adding slides. I only put this one in because it had umbra and penumbra. I forgot I'd already talked about it. The picture on the left is a good quality picture of what occurs during a total eclipse. I wasn't at the telescope during the total eclipse. I was told you could actually see, that is, Alex was the one that was at the telescope during the total eclipse. And he said you could actually see, my brain goes crazy, like solar flares. You could see red thing streaming up from the surface. It was really cool because you're blocking all of the direct sunlight. And the light you're seeing is coming from the atmosphere around the sun. And so here you're seeing the corona, the crown around the sun. And the picture on the right is obviously in the early stages of the partial eclipse. So you see most of the sun. That yellow thing is not an egg yolk. That's the sun. And yes, I took that with my iPhone camera looking through the telescope.
That's the sun? That was from your phone?
Yeah.
What? Oh.
And let's see. Where is the zoom button? Oh, that's really weird. Sometimes it shows up and sometimes it doesn't. There it is. Did you guys see the zoom button? You can tell I have lots of things to learn still. I don't know how it sometimes shows up. Okay, I'm not going to worry about it. I wanted to try to zoom in on this, but we just won't. But there is something inside of that circle. Can you see that? That's a sunspot. That was a storm that was occurring on the sun during the eclipse. And what's causing this right here? That is the moon blocking the sunlight. It's blocking part of the sun. Now let's talk about lunar eclipses. Actually, I've got lunar eclipses, then I'm going to go to something else, then I'm going to come back to lunar eclipses again. Lunar eclipses were important for historical understanding of the Earth. One of your reasons to understand that the Earth is a sphere is by looking at the shape of the shadow that the Earth casts on the moon during a lunar eclipse. And of course, remember I said flat earthers don't even believe that the moon comes between the Earth and the sun. Hence, I don't know what they think is going on during these eclipse events, but it's not what we think. And so they would say, well, that's stupid evidence. It's not even doing what you think it's doing. I just have no idea what they think it's doing. Of course, I don't think they care what it's doing. They just are sure that it's not doing what we think it's doing. Okay, so a lunar eclipse occurs when the moon passes into the shadow of the Earth. Now let's back up a step. What is the geometry for a solar eclipse? Where is the moon with respect to the sun and the Earth?
It shouldn't be behind Earth.
For a solar eclipse, it's not going to be behind the Earth.
Oh, for solar eclipse, that's going to be between.
Yeah, for the solar eclipse, the moon is between the Earth. What phase then is the moon during a solar eclipse? It's a new moon, because we're seeing the side the sun's not seeing if it's between us. For a lunar eclipse, where is it? Now what Alwan said before he realized the question.
It's going to be, Earth is going to be.
The Earth is between the sun and the moon. So what phase is the moon in that case? A full moon. So lunar eclipses only occur in full moons. Solar eclipses only occur at new moons. Except for in the movie Apocalypto. Did I talk about Apocalypto? Okay. In the movie Apocalypto, you have, I think it's supposed to be the Mayan culture. They have an eclipse. And they have gathered up all of these people who live in the jungles, and they're chopping off their heads to appease the gods. Because it's worldwide been a common belief that something like an eclipse must be that the gods are angry with you. You've done something to make them mad, so they're taking away the sun. And so you have to appease the gods. You have to do something to make them not angry with you. And what's natural? To kill people. Why? I have no idea. And so they're beheading all of these guys to appease the gods. And then the sun starts to come back. Huzzah! We've appeased the gods. So then what do you do with all the remaining people that you have collected up? And in the movie Apocalypto, they tell them they're free to go. But the warriors that collected them don't want to just let them go. They want to have some fun. So they make them run one at a time down this field, and they're shooting at them with bows and arrows until they kill them.
I think I've seen
And then our hero runs in a zigzag pattern instead of just sprinting as fast as he can. And they miss him, and he gets to the end of the field, and then they start chasing because they're angry because they weren't able to kill him. And that night, he is able to see because of the full moon. What phase does the moon have to be if you have a solar eclipse? New moon. You can't have a full moon that night. But you know, Hollywood doesn't pay all that much attention to science. So, how much time is there at minimum between a solar eclipse and a lunar eclipse?
Don't lunar eclipses tend to last longer than solar?
Lunar eclipses do, that's not the question here, but they do. And I'm glad you reminded me, I will say that, or talk about that after we answer this. What is the minimum time that you can have between a solar eclipse and a lunar eclipse? About 2 weeks. Because the period from full moon to full moon is what, 29.7 days or something like that? Yeah, I think that's right. And so half of that is just about 2 weeks. Okay, going to what Alban said, the shadow of the Earth is very big compared to the moon. The shadow of the moon was small compared to the Earth. So it takes a while for the moon to go through the Earth's shadow, and the entire moon can be in the Earth's shadow at the same time, easily, for a long time, like for an hour. What time of day does a lunar eclipse occur? At night. It wouldn't have to, but you're only going to see it if it occurs at nighttime. But if it's nighttime and the eclipse occurs, you can see it. Because if it's nighttime, that means you're on the side that's away from the sun. And if the moon is opposite the sun, moon is in opposition in other words, then if it's nighttime, you can see the moon in that arrangement. So if there is a lunar eclipse and it's nighttime for you, you can see it. On average, half of us on Earth, well, half of the Earth is at nighttime. So at any given instant during the lunar eclipse, on average, half the people on Earth should be able to see it. So are lunar eclipses commonly seen or rarely seen? Very commonly seen, because half the people can see it at any given time when there's a lunar eclipse going on. Whereas the solar eclipse, seeing the total solar eclipse, is very rare, because you have to be in that small region to see it. Okay, see, this is my last, actually it's not, I put a few more slides after this. Yeah.
So then, I want to ask a question of, so is there solar eclipses that happen in different parts of the world often, or like, because I know that we won't always see it, but like.
You are segueing nicely into what this slide is dealing with.
Okay.
So, I don't know if it's pronounced Chaldean or Chaldean, to be honest. But you know who these folk are, right? The ones that Daniel was trained with. The ancient astronomers determined that every 223 synodic months, which turns out to be 18 years, 11 days, and 8 hours, it could be 10 days or 11 days, depending on our leap day, how many leap days come in between. You will have a repeat of the geometry that created the eclipse. So you have a repeat of the geometry, but notice it's in 8 hours. How much does the Earth rotate in 8 hours? Actually, a third. Goes to a third of a rotation in 8 hours. So that means that this repeat of the eclipse is going to occur 1/3 of the way around the Earth. So it won't be at the same place. So you can't stay here in Lincoln and wait 18 years, 11 days, and 8 hours and have the eclipse occur again, because it'll be 1/3 of the way around the Earth. But of course, if it's 1/3, if you wait 3 of these cycles, so 54 years, in 34 days, you should have the same eclipse repeat again. Now, there's going to be slight variations because of some other things. But the eclipse will repeat again in 3 Saros cycles in the same location. So 54 years and 34 days, the same place in theory has the same eclipse. And so we can take the orbit of the sun, the orbit of the moon, and we can calculate when each eclipse will occur. And then once you've gone through a cycle, they'll just repeat. Now I want to talk about why eclipses don't occur every month. What did we say the moon's phase was during a solar eclipse? New moon. And during a lunar eclipse? Full moon. So why don't we have a lunar eclipse every full moon? Why don't we have a solar eclipse every new moon? Is what? Okay, the orbits aren't perfectly aligned. Oh, I have that slide after these two slides. I don't want to go back in the slide, so I'm going to do this and come back to that thought. I'm sorry. This here is a map of all the solar eclipses, actually all of the total solar eclipses. You can see down there, annular eclipses are in orange. You see any orange? No. All of the annular eclipses are removed, and then hybrids are also removed. So this is only the total eclipses occurring from 2001 to 2025. And so you can see on there the Great American Eclipse right there. You can see this one here, April 8, 2024.
I was there for the 2006 one on over India and Nepal. 2006 July 22.
Oh yeah, that is 2006. This one here.
Yeah.
So where were you for that?
I was in Nepal. That's where I.
In Nepal. So Nepal is right around there, right?
Yeah.
Actually, no, a little bit over here more.
Yeah. It wasn't like total, but it was like close to it.
Yeah, I mean, it looks like it would have had totality at least in part of Nepal.
Yeah.
So you're just traveling around from eclipse to eclipse.
Yeah.
Yeah.
So it's kind of cool to see those, and you can see, wow, there's only two there that go through North America. Can you see a repeat of the one that is going to occur in 2024?
What do you mean?
Okay, the 2024 eclipse is the remaining one in red. Can you see a repeat of that eclipse?
Oh, 2006 March.
Yeah, the March 2006 one.
Yeah.
Remember, it should be a month and 18 years was 18 years and 11 days. And so March must be 29. Yeah, March 29 to April 8. I think it's hard to read those dates.
And the one over Antarctica.
And then you have this one. It's not Antarctica, but
What is those dark, the thicker lines? What are they?
I think this is the same one that I just marked. It doesn't seem like, no, that's not 18 years.
Oh, the ones in Antarctica.
That's not 18 years. That's not the same one. Okay, the ones up. Let me talk about those then. Important thing there was to see that we have a repeat of the eclipse with a third of the way around the Earth. Okay, the ones at the Arctic and Antarctic. First of all, you have a distortion in our maps. You might have heard people talk about that our maps are diminishing the importance of places like Africa. Africa is bigger than you think it is. Why? Because our maps really magnify things in the poles and diminish stuff in the equatorial regions. And so Africa is bigger than you would think if you were comparing the size of the continent to the size of, let's say, North America, because of its location and the way we draw maps. Now, if you look on a globe, the globe is spherical and is not distorted. The problem is you have to take something that is spherical and try to make it flat. And you have different ways of trying to do it. But that comes into play when we look here at the Arctic and Antarctic eclipses. They look much bigger, number one, because you are just exaggerating on the map. But they also are actually bigger. So you have two things. They are actually bigger and it's distorted. They're also bigger because if you're at the pole, you're hitting it at a 23.5-degree angle, so it's more spread out. Hence, remember, we talked about less direct sunlight because of that. A bigger shadow region because it's spread out as well. So there's two things going into play. And some of these, the geometry is right that they actually go backward. The eclipse that we had here went like that. Well, you can have some of these polar ones that go the opposite direction because of the geometry. Zooming into the United States, this is 2001 to 2050. The last one was 2001 to 2025, I think. Here are eclipses that are going to be crossing the United States, what we're really interested in. And once again, we have the total eclipses are blue, and the annular eclipses, they've got to be red outlined with yellow. And so we had this one here, and you see Lincoln is marked, the capital city called the Star City by geniuses here in Nebraska, is just inside the totality region. And you see this region here, totality for both the 2024 and the 2017. And then you have this big one here that's going to come by in 2045. I'll be an old codger then. You guys will be young bucks, around 50. That's young, right? That's how old I was for the Great American Eclipse. You can probably figure out my age now, right? So it's kind of cool to see those and, plan where you're going to be in 2017. Where do we want to go? Try to find some place in this region because that's where it's going to be good viewing. Actually, I think it's probably a little better down here. I haven't looked carefully. Okay, anyone remember what we were talking about? The geometry and why we don't have an eclipse, solar eclipse every new moon, a lunar eclipse every full moon. The reason is the geometry. In the picture there, it looks like you should every time because that's a two-dimensional picture. Let me point out, during an eclipse of the moon does have a red glow. It has the red glow because of the refraction, the bending of light through the Earth's atmosphere, the same effect that makes it so we see the sun when it's about 5 degrees below the horizon. Also is the effect that gives you an Earth glow on the moon during the eclipse. So here is the full explanation to my...
Why red?
Why red? Why is the sky blue? They are the same answer.
Is it because of the wave?
Well, it is because of the wavelength, because red is a long wavelength, blue is a short wavelength. We have in the air molecules of primarily nitrogen with some oxygen. 79% nitrogen, 21% oxygen. When light goes through those molecules, it scatters off the molecules. But those molecules are smaller than the wavelength of light. In such a situation, the scattering depends on the wavelength, such that short wavelengths like blue light are scattered much more effectively. So the sun, being virtually white, has this white light that comes into the atmosphere, and then the blue light is scattered largely away. It's like 16 times stronger scattering for blue light than it is for red light. And so the sky has like 16 times more blue light than red light, hence it looks blue. Because the sky, if you're not looking directly at the sun, all you're seeing is the scattered light. So the light that makes it through the Earth's atmosphere is the light that didn't get scattered all over the place, which is red. That's also why sunsets and sunrises you see red sun, because you're seeing the sun with more of the blue removed than normal because it's going through more atmosphere than normal. It's called Rayleigh scattering. Okay, so here's the answer of why we don't have an eclipse every new moon, every full moon. The moon is tilted about 5 degrees from the ecliptic. Remember, the ecliptic is the path of the Earth's orbit around the sun. The moon's tilted about 5 degrees from that. So the only time when you're going to get an eclipse is when the moon is crossing the ecliptic. Now, for the Earth when we see the sun crossing the ecliptic, obviously it's not the sun crossing. But when we see the equator and the ecliptic cross, that's the equinoxes. Essentially, for the moon orbiting the Earth, the only time you can have eclipses would be equivalent to the equinoxes. And so when the moon is crossing the ecliptic, it's an eclipse season. And it is a slow enough process that you can actually have a lunar eclipse and a solar eclipse that occur 2 weeks apart. It's going to work best if the solar eclipse is, of course, that's the one that has to be dead on. The lunar eclipse is off to the side of the moon because you've got a lot of wiggle room there. The Earth's shadow is big. So you have eclipse season when you have the moon is crossing the ecliptic. And I think I thought it was every 13 months. I can't remember when you have eclipse season. The end. Hey, I finished only 3 minutes early. I was thinking I was going to finish earlier than that. All right. You guys ready for a long weekend? Me too. Have a great one.